Now that we have some tricks for evaluating definite integrals, let's look at some applications of definite integrals, some things we can actually do with definite integrals. To start out with, let's have a deeper look at finding area between curves. So just a regular old definite integral gives us the signed area between curves, but what we're going to have a look at is some finer points of finding the absolute area between curves. In other words, the unsigned area between two curves. So here's the general setup. We have a couple of x values, a and b, and we want to know what is the area between these two graphs, y equals g of x and y equals f of x. So that's going to be this region in the middle here. And one important thing about this picture is notice that f is the one on top. Okay, so just keep that in mind. So in all of our applications of integrals, we'll sort of use the same general train of thought, which is what an integral does is it adds up infinitely many, infinitely small things. So what we can do to use an integral is take some problem, like this area problem, and break it down into infinitely many, very tiny pieces, and then use an integral to put those pieces back together. So let me explain what I mean. At every x value in here, between a and b, there is a little strip of area above that x value. Okay, so to know what the area of this little strip is, well, it's so narrow that it's pretty much a rectangle. So to get the area of this, we just need to multiply its width by its height. So what is the width of this infinitely narrow rectangle? Well, it's infinitely narrow, so we need some way of expressing the idea that the width of this rectangle is an infinitely small piece of the x-axis. And conceptually, the notation for an infinitely small piece of the x-axis is dx. Right? Really, in an integral like the integral from a to b of whatever dx, this comes from the limit as n goes to infinity of some Riemann sum. And then there's a delta x here. And the idea is when you take a limit as n goes to infinity, delta x turns into the infinitely small x interval dx. So we're sort of, this dx is really a shorthand for some sort of limiting process applied to delta x. But the width of this rectangle is dx. So to find, put a dx here. So to find the area, all we need now is the height. So the height of this infinitely narrow strip is from this spot down to this spot. So we need some way of measuring this vertical distance. And to measure a vertical distance, if you know the top and the bottom, you can just subtract the bottom from the top and you'll get the vertical distance. Well, the top is on the graph of f, so the top is f of x, and the bottom is on the graph of g, so the bottom is g of x. And that means that this height is f of x minus g of x. So here for the area, we need f of x minus g of x. And again, it's f of x minus g of x and not g of x minus f of x because f is the one on top. So the fact that f is the one on top is important here. So we've solved this area problem for one of these infinitely narrow strips. It's just f of x minus g of x times dx. And now we need to put together all of these infinitely many strips, right? There's one of these narrow strips for every x value from a to b. So we need to add up infinitely many, infinitely small areas. Notice that this area is infinitely small because it's some number, f of x minus g of x, times dx, and dx is infinitely small. So dx times f of x minus g of x is also infinitely small. So we need to add up infinitely many, infinitely small things. And that's exactly what an integral does. So if you ever find yourself in a position of wanting to add up infinitely many, infinitely small things, usually it's an integral that will get the job done. So a single area of one of these strips is f of x minus g of x times d of x. And so to add up all of these areas, we integrate from a to b. So this is the absolute, that is unsigned, area from a to b, and between f of x and g of x. And again, keep in mind that this part of what makes this formula work is the fact that f of x is above g of x. Okay, we'll see what happens if they trade places. It gets a little more complicated. But the general idea here is, right, inside this integral is just the area of a single strip, and it's the height times the width. One interesting thing about thinking of areas this way is that the differential shows up in a completely natural way. So the differential isn't just something you tack onto the end because I said you had to. The differential is there because it is the width of this rectangle. So if you omitted this differential and you wrote the integral from a to b of f of x times g of x, and you didn't write the differential, this would be the integral of just the height of the rectangle. But that doesn't make sense because, first of all, this isn't infinitely small, and second, it doesn't represent an area. So this sort of really makes it clear why you need this differential. The differential is required for this integral even to make any sense. So we'll look at some examples.